Hello everyone, I'm Matheus Campos and I'll be presenting this work with the title Numerical Analysis of an Alternating Current MAT Pump with Rectangular Section for Electrolyte Solutions. This work was made by me, Professors Gabriel Verissimo and Marcelo Colaço. So, to start the presentation, magnetohydrodynamics is the study of electrical conducting fluid flows in the presence of magnetic and/or electric fields. This theory has many interesting applications, but one that's particularly interesting for mechanical engineering is the MAT pump. It's a pump that uses the large force to pump the fluid. These pumps present some advantages when you compare it to their mechanical counterparts: simplified construction, absence of moving parts, reduction in noise production, and few others. These pumps can be divided into two classes: DC, direct current, or AC, alternating current. The alternating current configuration may be particularly interesting when pumping, for example, electrolyte solutions, where there is the occurrence of electrolysis, and currently, as a consequence, there is the formation of bubbles, and there is an accelerated electrode degradation. So we can use alternating current to inhibit electrolysis. But the use of alternating current implies in a different configuration in order to achieve the unidirectional flow and preventing backflow. So it can cause some implications in the flow, and the principal aim of this work is to evaluate what is the influence of the alternating current over the flow. The channel studying this work is based on the one proposed by ELA in 2013, and we can see here in figure 1 the channel we will use in this work. We assume that the fluid is Newtonian and the fluid is incompressible. Then the continuity equation reduced to the presented here in 1. In the momentum equation, there is an additional term for the Lorentz force, the cross product between current density and magnetic flux density. Here in the energy equation, we introduce the Joule heating effect. To calculate the current density, we can use the Ohm's law, and due to the low frequencies, low magnetic flux density, low velocities, and the fluid physical properties, we can evaluate these two terms for the induced electric fields before the one imposed by the electrodes. In order to obtain the electric potential, we will also need the Poisson equation for the electric field. Geometry design, meshing, and physical modeling were made in Encit. We used the simulations and Fluent 2019. The software allows the user to introduce additional terms to the conservation equations. So we used it to introduce Lorentz force in the momentum equation and Joule effect in energy equation. There is an additional tool called user-defined functions that allows the user to introduce additional transport equations and use it to solve the electric Poisson equation. Inside UDFs, you can also solve the Ohm's law to calculate the current density. The magnetic flux density, as I said before, it's considered to be uniform and known in the entire domain over time. The fluid properties are shown in table 1 that we used. It's the properties for seawater. We also evaluated during validation step different turbulence models, so use the lambda model, standard K epsilon, realizable K epsilon, RNG K epsilon, standard K omega, SST K omega, and transition SST. For each model, we run a convergence analysis to choose the best mesh for each one. The model validation consisted in a comparison between simulated results and experimental data available in our 2011 work. We followed the guidelines presented by the author for both the experience and the boundary conditions. In this work, our key used a DC pump operating with two different voltages of 12, 20 and 30 volts. As can be seen, there is a reasonable agreement between experimental data and simulated results. There is the formation of the end velocity profile for every model simulated, and this is a characteristic of this kind of flow. We can see that the best results are achieved for the standard K epsilon and RNG K epsilon models. And once the RNG model requires a mesh with less refinement, we choose to proceed with this one for the AC pump simulations. We also made energy equation validation, but we call it a qualitative validation once the working does not present sufficient information about the temperature measurement or the boundary conditions. So here we presented this comparison between simulated temperature and experimental temperature. We can see that both behavior and values have great agreement. In order to evaluate the alternating current effects in the AC and AD pump flow, velocity, pressure and temperature profiles are obtained for a peak applied voltage of 30 volts and for frequencies of 1 Hz, 10 Hz and 50 Hz. The results are measured during a complete period of voltage oscillation, so we can make a proper comparison. We compare these values for a DC equivalent case. This case is the one where the Lorentz force, the average of the Lorentz force during one oscillatory period is equivalent for the DC and AC case. As boundary conditions for these simulations, we use the impenetrable walls and no-slip conditions for the channels, side walls and bottom, and for the channels top we use a stress-free condition. For a critical case we use a thermal, and consider that the channel is thermo-insulated in every wall. Also we select the known pressure in the inlet, static pressure, and the outlet dynamic pressure as the boundary conditions. And for the electrodes we select one with zero electric potential, and the other one we use a sinusoidal function where 30 volts used as peak voltage. For the magnetic flux density we consider as uniform in this magnetic domain and zero outside that, and it varies synchronously with the applied electric potential. Current density, Lorentz force, velocity and temperature are evaluated along channels width in the pump outlet, while the pressure is evaluated along the channel's length close to its center. Here for current density you can see that this profile is formed and repeats for every frequency, and there is no significant difference between the values, and the maximum occur close to the electrodes in the walls, while the minimum values are reached in the center. This kind of behavior will repeat for the Lorentz force. Once the Lorentz force depends on the current density. We can see that both for current density and Lorentz force there is a great agreement between the profile formed for both DC and AC cases, and you can see that the oscillation caused by the applied voltage will make the Lorentz force oscillate over time. And you can see there is a symmetric behavior along the period, and once again there is no significant difference for the evaluated frequencies. Here in figure 5 let's show the results for the pressure distribution. along the channel's length. It can be observed that the profile for the AC case is matched the one for the DC configuration, although there is that oscillation caused by the applied voltage and magnetic flux density. And while for the current density and the Lorentz force, the observed oscillation is symmetric over the evaluated period, this does not happen for pressure, and it occurs because of the inertial effects. You can also notice that while for these two first quantities, the current density and Lorentz force, there is no difference in the results. For the three evaluated frequencies, for pressure results, there is a significant difference, especially for the lowest frequencies. While for the highest frequency, there is a great agreement for both DC and the intermediate values of the sine function. For the lower frequency, it does not occur. Here in figure 6 we can see the results for the velocity profile. We can see that the velocity profile is formed due to the Lorentz force, as we saw 8 right values are close to the wall. For the right frequencies, there is a satisfactory agreement between the direct current case and the alternating current case. And mainly it's possible to observe that for frequency over 10 Hz, there is a lower amplitude of oscillation. Here in figure 6, we can see the velocity profile formed at the pump's output. We can see the profile assumes the N form, and it's caused due to the Lorentz force. As you saw, it's higher close to the electrodes, which leads to these velocity peaks close to the walls. And for the right, the highest frequencies, there is a great agreement between the DC and AC case, while for the lower frequency there is a high amplitude in the velocity profile oscillation. For frequency around 10 Hz, this oscillation is not significant, while for 1 Hz it's quite high. Here in figure 7 we present the temperature results. The profile observed is the same that for the current density, and the highest temperatures are too close to the walls where electrodes are located, and the current density is more intense. The profile is matched for both alternating current and direct current case, although we can see here for the frequency of 6 Hz that for the alternating current, highest temperatures are achieved. As a complement to the results presented before, we can calculate the pump efficiency for both DC and AC case, and due the energy dissipated to Joule effect, we can see that the efficiency for the AC configuration is half the one for the DC configuration. And as a conclusion to this work, we can see that in the results presented that current density, Lorentz force, temperature and pressure presents an oscillatory behavior for the EC case that also happens for the velocity profile, but for frequencies over 10 Hz there is no significant variation in the velocity profile, while for those quantities there is a significant variation. We can also see that for higher temperatures, for the AC configuration, we reach higher temperatures and lower efficiency. Here we proceed to show you the reference used in this presentation, and thank you for your attention.